speaking about some connections between two different topics we've been hearing about at this year's UTL and some other years. Firstly, this area of general probabilistic theories, or perhaps operational probabilistic theories that we met on Monday. And secondly, these categorical approaches we've heard more about today, and particularly a flavour called effectus theory that maybe some of you met at last year's UPL. In more detail, I'll introduce the sort of variant of the idea of these OPTs, a notion of an operational theory, and see how we can study these things just as special types of categories. So we already know that we can treat sort of compositional aspects of these theories using a notion of a symmetric monoidal category. And here we'll just be saying that we can capture other aspects of these theories, such as their tests, using these other features you see here. And we'll roll those up into what we'll call an operational category and see how those correspond to these theories. So thanks to the nice introduction we had from Obian on Monday, I think that can be relatively quick. We're talking about these theories. So I'll call these operational theories with control. The basic ingredients are physical systems and physical events between them. And we can compose these side by side and one after the other, and this lets us depict these events using these nice circuit diagrams that we're used to seeing by now. So basically we're going to apply they form a symmetric monoidal category. The theory also talks about tests. So we think of a test like this as being a finite outcome measurement we perform on this system A. We get one of our little outcomes from this set X, and that means the event Fx takes place. Now we're left with this system Bx. So something slightly different from OPT is that I'm letting the output type of the system vary depending on the outcome. For example, we might have your system destroyed with one outcome and preserved with another. It's up to the theory to say which collections of events form tests. More generally, here I'm going to be calling subsets of tests partial tests. The final feature of one of these theories that's maybe less obvious is called coarse graining. And this is the first way that you can use this data from tests operationally, and it just says you'll have to throw some of it away. If you have a test where two events are of the same type, operationally you can imagine doing that test and then just throwing the information away as to which of those two occurred. So really you've taken those two events and you've merged them into a new one that we denote with this circle with V symbol, and that actually is related to the notation from the last talk, conveniently. So it has a partial addition operation on these events, so it's defined whenever they belong to a test together. I need to make a couple of basic assumptions along with these. So I assume I have units for this coarse graining operation that we just think of as impossible events between any two systems. The main assumption is called control, and we met this on Monday in the name of conditioned tests. And it just says that you're allowed to perform a test, and then conditioned on that outcome, choose how you behave next. So you can pick which test you're going to perform next, and that whole procedure is something that you can do operationally. So this collection here needs to also form a test. And we heard that this is closely related to a notion of causal structure in your theory, which also meant that every system comes with a unique deterministic effect. So an effect is an event into this trivial system I, and deterministic means that on its own it forms a test. But finally, we'll actually assume a slightly stronger statement than causality. We'll assume every event comes with a unique effect which pairs with it to form a test, and to get causality out of that, you just take your original event to be the impossible one. And that's really the end of our main assumption. So crucially, we're not assuming any explicit probabilistic structure in these theories, as one normally does. There's obviously many examples of these. So some of the more probabilistic style ones, you can treat classical physics or probabilistic physics, or quantum theory, where your events would be completely positive maps and they'd be subunital because they occur with some probability, and you could take your objects to be Hilbert spaces or C-star algebras of really any dimension. So now the aim is just to talk about how we can treat one of these theories in a completely categorical way. And the idea is that instead of talking about this outcome data, just encode that information in the systems or in the objects. So we're going to talk about theories with this property of having what we'll call direct sums, perhaps slightly dodgily, saying that every finite collection of systems comes with a bigger system, here called B, and a test which projects onto each of those factors. And it's such that instead of talking about partial tests of that output type, you can just talk about individual events going into that bigger system that project to give you the events of your test. So we think of this as just a way of adding together these systems in a sort of non-interacting way. And you can see that if you have this property, things will become simpler because instead of talking about these tests and so on, you can just talk about individual arrows in your category. But the point is that it's also natural because starting from any theory, you can always pass to a completion. It's called pizza plus. It does have this property. So in this new theory, I'll just say what its events are, and they're what you might call the category of partial tests of your original theory. So basically the events in the new theory are partial tests, but more detail here. The systems will be index collections of systems of your first theory, and the events between them will be sort of controlled partial tests. So each input bit X specify a partial test of the type that makes sense. You can think of that as a a big matrix where each column is a partial test. And to compose these, you just use matrix composition along with your coarse graining. So the point is, if we didn't have these direct sums around, this new theory does have them, and if they're already there, then both theories are equivalent. So for now, we'll just assume we have them, and that's the last assumption, really. And the point is that we can describe these using a basic categorical notion, namely that they form finite co-products in that category of events. So co-product is just a way categorically of adding together some objects in a sort of disjoint way. It always comes with these co-projection arrows that we see here, and they satisfy universal property. Here, because we have these zero arrows around, we also get maps coming out of these co-products, and we already met them in the definition of a direct sum. So if you start from the definition of a direct sum, this tells you how to define your co-projections, and you can go back the other way. And the point is that this structure is all we need to describe all the interesting stuff of our theory. So we've already seen that instead of talking about these partial tests, we can just talk about arrows going into these co-products that project in the appropriate way. You can detect when one of those is a test categorically. You just require that arrow F above there to be causal, or here I use the word total, so it just needs to preserve discarding. So intuitively, a test as a whole is a deterministic process because you always get one outcome occurring, and that's just captured by this equation here. You can also describe coarse graining nicely. So the kind of partial test you can coarse grain over is, consists of a load of events of the same type, so it'll look like this arrow F here, going into a co-product of something of itself lots of times. And then you just want to merge all those different outcomes into one thing. And when co-products are around, you always have this co-diagonal map defined in your category, which sort of intuitively merges those factors together. So the theorem says, instead of talking about a theory with this property of having direct sums, you can just talk about a special type of category that here I'm calling an operational category, but one in partial form, and we'll make sense of that in a second. I quickly mention the total form. But in more detail, it's a symmetric monoidal category. It's got these finite co-products and these zero arrows, and so zero object. It also comes with these discarding maps, so we need to impose them as some extra structure for now. And it satisfies some conditions. So the first one says that the projections we had out of these co-products are jointly monic. So that means if I have two arrows coming into this object here, and they project in all the same ways, then they'll in fact be equal. So intuitively, that would be like having two partial tests that have all the same outcomes. And so we would take those to really be the same partial test, so they should be equal. Other than that, there's just this condition that encodes the law we already met, which said that every event pairs with a unique effect to form a test, and that's just this stated in this new language. And finally, just some basic compatibility conditions between these structures, between the tensor, the co-products, and the discarding. But these aren't the more interesting ones. So starting from any one of these theories, we know its category of events has all these properties. And more interestingly, just a category, any category with these properties gives you enough structure to define the theory. So you can define the partial tests by defining them to be arrows coming into the co-product in this way. You can define the tests using your discard maps, and you can define the coarse graining using your co-diagonals. So it's really a two-way correspondence we have between both of these notions. Now there's another way, if we think about what we did, we started from our category and passed to its completion and said that thing was just described by one category, the category of events. That was the category of partial tests of our original category. You can do the same thing instead working with what you call the category of tests of your original category. So again, it would be like matrices in which each column just forms a test. And that gives us, we can play the same game with that, and it gives us what we call the operational category in total form. So that's a symmetric monoidal category. Again, these co-products exist and they encode the way data flows into tests. And instead of talking about these discarding maps, we can just capture causality by saying that this tensor unit I is a terminal object. So that means every object comes with a unique arrow into it, and that's because precisely every system comes with a unique deterministic effect. And again, it has to satisfy two conditions, which I've just put up here, but we won't have too much time to explain. The point is that these are very closely related to a notion of an effectus due to Bart Jacobs and his students in Nijmegen. And in particular, any one of those categories forms an operational category in this form. And the notion of total and partial versions of these categories is coming out of Kent and Cho's work in that area. So if you're already interested in that approach of treating a categorical logic style approach to these things, then another way you can look at one of those categories is as a certain type of operational theory with these properties. summarize all the correspondences here. Start from your theory, pass to this new one with the direct sums, and you can describe that thing equivalently as one of these operational categories in either of these two forms. And all of this can be made into nice appropriate functors between categories, which is what these symbols are supposed to be denoting here. Just for some examples, since we haven't really had too many, if you wanted to treat classical deterministic physics, let's say, you end up with the operational category of sets, and the partial one would be partial functions. For quantum theory, you can take, say, something like C-star algebras with completely positive unital maps for the tests, the deterministic things, and the partial things would be subunital maps. And in fact, both of these are effectuses. So just to say why one would want to think about these things, firstly, if you're already interested in or know about effectus theory, it gives you this operational interpretation I mentioned. More generally, because it's completely categorical, you can hopefully start providing some connections between, say, CQM, the categorical quantum mechanics program, and general probabilistic theories. In more detail, what's really happening is we're separating out the different aspects of an operational theory. So we already knew that we could do the compositional aspects using the notion of the monoidal category, and now we're just saying that we can also treat the control aspects, so the tests and the coarse graining and all of these things, again using other categorical features, which are what you get in an operational category. Finally, you just typically then say that you have explicit probabilistic structure around, but for many of the arguments you make with an OPT, let's say, you don't really need all of the full structure of real numbers and so on. And so with that in mind, what would be good is to think about how much of the original work that was done with those theories in terms of these quantum reconstruction theories can be lifted to this more general setting. So thanks.
Questions? Comments? Yes?
So you have this partial addition.
Yeah.
So you take this as an assumption that you have this?
Yeah, I mean, if you, in any OPT, they sort of also assume this, but they already explicitly are working with probabilities and linear acts, essentially, so they're just adding them together.
Right.
So here it's just taken as an assumption that you can, operationally, if you have a test, you can merge two outcomes if they're the same, because that's just throwing away some data in the lab, essentially.
So when you have direct sums and you have this partial addition, does that make your category a unique decomposition category or something like that?
I don't know the definition of unique decomposition category.
Oh, we can talk about it afterwards.
Yeah. Might be good.
That's like Verdi or something like
Yeah,
that.
exactly.
Yeah. Any more questions, comments? Oh, okay. So, I think a lot what you do here is spelling out things which these people leave very implicit because they like to be precise about things.
Which people?
This OPT, GPT.
Yeah.
They love to call things actions and then other stuff around which they don't call actions or even don't specify but use it. And here it's all explicit.
Yeah, I mean, it's trying to formalize what an operational theory is and try and make it a bit clearer. That's the idea. Yeah.
Okay, thanks Sean again.